Hello and welcome to English Plus Podcast. I'm your host Danny, and today we're embarking on an intellectual adventure to explore one of the most groundbreaking concepts in physics, Einstein's theory of relativity. This theory, which comes in two flavors, special and general relativity, has transformed our understanding of the universe. So buckle up as we dive into the world of bending time, warping space, and everything in between. Let's start with special relativity, which Einstein introduced in 1905. This theory fundamentally changed how we think about time and space. Prior to Einstein, Sir Isaac Newton's view of an absolute universe reigned supreme. Time ticked uniformly, and space was a fixed stage upon which the events of the universe unfolded. Enter Einstein with a mind-bending proposition. Time and space are relative. They're not fixed, but vary depending on your speed and gravity. Imagine you're standing still, and a friend zips past you in a spaceship at close to the speed of light. According to special relativity, time for your friend on the spaceship would actually move slower compared to yours. This isn't just theoretical. GPS satellites orbiting Earth at high speeds experience time slightly differently than we do on the ground. Without adjustments for this time dilation, our GPS readings would be off, leading us astray in our travels. Fascinating, isn't it? And now let's amp up the complexity as we move to general relativity, introduced by Einstein in 1915. This theory extends the principles of special relativity to include gravity, which, according to Einstein, is not a force but a curvature of space-time caused by mass. Think of space-time as a fabric. Place a heavy object, like a planet, on it, and the fabric curves. This curvature is what we experience as gravity. Or at least that's what general relativity is all about. Now consider the way astronauts float in space. It's not that there's no gravity up there, it's that they're in free fall, moving along the curved space-time created by Earth's mass. The same principle explains why light bends around massive objects like stars or black holes, a phenomenon known as gravitational lensing. This bending of light was one of the first proofs of general relativity observed during a solar eclipse in 1919. The implications of general relativity are profound. It predicts the existence of black holes, regions in space where gravity is so strong that not even light can escape. It also leads to the possibility of wormholes, theoretical passages through space-time offering shortcuts across the universe. Mind-blowing, right? But what does all this matter in our daily lives? Well, aside from making our GPS systems accurate, relativity has broader implications. It shapes our understanding of the universe, guiding astrophysicists in their quest to unravel cosmic mysteries. From the expansion of the universe to the behavior of galaxies, relativity is the rule book by which the cosmos plays. And now I want to leave you with a thought. The theory of relativity, once a radical and abstract idea, is now a fundamental principle that shapes our understanding of the universe. It stands as a testament to human curiosity and intellect. I encourage you to look up at the stars tonight and ponder the incredible nature of our universe shaped by the principles of relativity. And now, of course, we are English Plus and things don't end with our just talking about the topic. We will dive a little deeper into the keywords, practical applications, and we will also answer some of the commonly asked questions, and we might also debunk a myth or two about Einstein's theory of relativity along the way. So don't go anywhere, as we will focus on some keywords next. I'll be right back. In today's discussion, we delved into some truly fascinating concepts from Einstein's theory of relativity. As we unpack the depth and implications of this groundbreaking theory, let's highlight and define some key terms and phrases that are pivotal to understanding the essence of this discussion. We began with the term theory of relativity, which, in its simplest form, refers to the idea that the laws of physics are the same for all non-accelerating observers. This theory, presented by Albert Einstein, revolutionized our understanding of space, time, and gravity. And there's also the special relativity, a subset of the theory of relativity, fundamentally altered our perception of time and space. It's based on two postulates. The laws of physics are invariant in all inertial frames of reference, and the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or observer. And there's general relativity, which extends these concepts, introducing the idea that gravity is not a force, but rather a curvature of space-time caused by mass. This was a radical shift from Newton's law of universal gravitation, leading to new ways of looking at the cosmos. We also discussed time dilation, which is a phenomenon in special relativity where time slows down for an object in motion relative to a stationary observer. It's a concept that has practical applications, such as in the functioning of GPS satellites. And of course, there's also gravity. But in the context of general relativity, it is described not as a force, but as the curvature of space-time. This redefinition of gravity is one of the key aspects of general relativity and has profound implications for our understanding of the universe. And there's the term space-time, which refers to the four-dimensional continuum in which all objects in the universe are located. In relativity, space and time are not separate entities, but are interwoven into a single continuum. We also talked about gravitational lensing, which is another fascinating concept, and it occurs when a massive object like a galaxy or black hole bends the light from objects behind it. This effect has been used to study distant galaxies and to provide evidence for general relativity. We also touched on black holes, and these are regions in space where gravity is so strong that nothing, not even light, can escape. The concept of black holes emerged from the equations of general relativity and has captivated scientists and the public alike. We also talked about wormholes, which are theoretical passages through space-time that could create shortcuts for long journeys across the universe. While still in the realm of theory, wormholes stem from the equations of general relativity and continue to intrigue scientists. And lastly, there's the expansion of the universe, which is a concept that has been shaped by the principles of relativity. It refers to the observation that galaxies are moving away from each other, suggesting that the universe is expanding. And weaving these terms and concepts together, we see a tapestry of ideas that not only redefine our understanding of the universe, but also continue to inspire awe and curiosity. The theory of relativity, with its profound implications for how we perceive time, space, and gravity, serves as a beacon of human intellect and the relentless pursuit of knowledge. As we ponder these concepts, we're reminded of the limitless potential of the human mind to explore and understand the mysteries of the cosmos. And now, my friends, it's time for us to discuss some real-life applications to this theory put forth by none other than Albert Einstein. That's coming next, so don't go anywhere. I'll be right back. In our exploration of Einstein's theory of relativity, it becomes evident that this groundbreaking theory is not just a highbrow scientific concept relegated to the realms of theoretical physics. Instead, its implications and applications permeate our daily lives in ways we might not immediately recognize. Let's begin with the idea of time dilation in special relativity. This might seem like a concept straight out of a sci-fi novel, but it's actually a practical consideration in the functioning of the Global Positioning System, or GPS. The satellites that provide GPS data are moving at high speeds and are located in a weaker gravitational field compared to the Earth's surface. According to relativity, time ticks slightly faster for these satellites than for clocks on the Earth's surface. If engineers didn't account for this discrepancy, the GPS calculations would be off by several kilometers. Every time we use a navigation app on our smartphones, we're indirectly experiencing the reality of special relativity. So next time you use GPS to find your way, remember you're witnessing the principles of relativity at work. And moving to general relativity. Its understanding of gravity as the curvature of space-time brought about by mass has profound implications in astronomy and cosmology. The concept of gravitational lensing, for example, allows astronomers to study objects that are too far away to be seen directly. By observing how the light from distant stars is bent around massive objects like galaxies, astronomers can map out the distribution of dark matter, which doesn't emit light and is invisible to traditional telescopes. For those interested in stargazing or astrophotography, understanding this phenomenon can enrich your appreciation of the night sky. And furthermore, general relativity's predictions about black holes have been a cornerstone in the search for understanding the universe's extreme conditions. The first ever image of a black hole captured by the Event Horizon Telescope not only confirmed Einstein's predictions, but also provided crucial insights into the behavior of these mysterious entities. For students and enthusiasts, this is a vivid example of how theoretical physics can lead to groundbreaking discoveries. And then there's the expansion of the universe. Understanding that the universe is expanding and the rate of this expansion has implications for the ultimate fate of the cosmos. This concept, rooted in the principles of relativity, is essential for anyone interested in cosmology. It provides a framework for understanding the past and future of our universe, encouraging us to think about our place in the cosmos. In practical terms, these concepts from the theory of relativity inspire us to look beyond our immediate environment and consider the broader implications of our actions on a cosmic scale. They encourage critical thinking and a scientific mindset, which can be applied in various fields and everyday problem solving. Now, for action points, consider engaging with these concepts further. If you're a teacher or student, you can incorporate the real-life applications of relativity into your curriculum or studies. For those in software development or engineering, understanding these principles can be crucial in designing more accurate systems like GPS or astronomical tools. And for the curious minds, simply looking up at the night sky with a newfound understanding of the universe can be a profoundly enriching experience. In sum, the theory of relativity, far from being an abstract set of ideas, is deeply embedded in our everyday experiences, guiding the technologies we use and shaping our understanding of the universe. Its study is not only an intellectual pursuit, but also a practical one, with applications that touch upon various aspects of our lives. And finally, in our very last part of our episode today, I will answer some of the most commonly asked questions about Einstein's theory of relativity and debunk some myths revolving around it as well. That's coming next, so don't go anywhere. I'll be right back. As we delve deeper into the intriguing realms of Einstein's theory of relativity, it's natural for further questions and curiosities to arise, along with some common misconceptions. Let's address these in a manner that deepens our understanding and clears up any lingering doubts. One question that often comes up is, if time dilation occurs, does this mean time travel is possible? Well, it's a captivating thought, straight out of science fiction. Time dilation does indeed suggest that time can flow at different rates under extreme conditions, such as near the speed of light. However, this doesn't imply time travel in the sense of moving back and forth through time as portrayed in movies. The kind of time travel allowed by relativity is a one-way journey into the future, with no return ticket to the past. So for sci-fi fans, I'm sorry, but that's what we've got so far. If we have anything in the future to suggest otherwise, I'll be sure to include it in a new episode. Well, let's move to another question. Another common question is about the speed of light. Why is the speed of light the ultimate speed limit? Well, according to special relativity, as an object approaches the speed of light, its mass effectively becomes infinite, and it would require infinite energy to move it at the speed of light. This universal speed limit is not just a speedometer reading, it's a fundamental property of the universe. And people often wonder, how does relativity affect our understanding of the universe's age and size? Well, general relativity has significantly influenced cosmology, which is, by the way, the study of the universe's origin and evolution. It suggests that the universe is expanding, which has led to the Big Bang theory. The rate of this expansion, governed by relativity, helps us estimate the age and size of the universe. And another curious inquiry is, can relativity explain gravity in all situations? Well, while general relativity has been incredibly successful in explaining gravity in most contexts, it struggles at the quantum level. This has led scientists to search for the theory of quantum gravity that can marry the principles of quantum mechanics with general relativity. And now, for those of you who are wondering about quantum mechanics or quantum physics in general, it is definitely a topic for another episode in our series Big Ideas Explained. Anyway, let's get back to our commonly asked questions and misconceptions. Many ask, how does relativity impact modern technology? Now, apart from GPS technology, relativity also plays a role in technologies like particle accelerators, which are used in medical treatments and research, and in predicting the behavior of objects in space, which is crucial for space missions and satellite placements. Now let's talk about a frequent misconception. Some people say that relativity only applies to objects in space or at high speeds. Well, in reality, relativity impacts everyday life. For example, the time dilation effect, while minuscule, affects the precision of atomic clocks, which are essential in synchronizing time for various technologies and scientific measures. So again, it is definitely minuscule. We can't even notice it, but it's very important for the atomic clocks. And now, another question is about the practicality of wormholes. Are wormholes a reality? Well, while wormholes are a theoretical possibility in general relativity, there's no empirical evidence for their existence. They remain a fascinating concept, but are currently relegated to the realm of theoretical physics and science fiction. And let me stress here on the idea "so far," because who knows what happens in the future. We might actually have empirical evidence for their existence in the future, but so far, no empirical evidence, just theoretical physics and, of course, science fiction. Now, people often ask, is it possible for something to escape a black hole? Now, according to general relativity, nothing can escape a black hole once it crosses the event horizon. However, theoretical physicist Stephen Hawking proposed that quantum effects could allow Hawking radiation to escape black holes, a concept that is still under active research. But it is a possibility, who knows? Remember, all great ideas that we now take for granted started as theories. So while some of these theories may be proved wrong down the line, but other theories we take today as facts. So who knows? The late Stephen Hawking might be right. Now let's move on to another question. A question related to the universe's fate. What does relativity say about the end of the universe? Now, while relativity contributes to our understanding of the universe's expansion, it does not definitively predict its ultimate fate. Theories range from a big crunch scenario to an ever-expanding universe, but the exact outcome remains one of cosmology's biggest mysteries. And finally, a common myth is that Einstein's theories are just theories and not proven. Well, in fact, both special and general relativity have been confirmed through numerous experiments and observations, from the bending of light during solar eclipses to the detection of gravitational waves. In addressing these questions and misconceptions, we gain a fuller appreciation of Einstein's theory of relativity, its implications, and its limitations. It's a theory that continues to challenge and expand our understanding of the universe, sparking as much wonder today as it did over a century ago. As we bring this episode to a close, I want to leave you with more than just thoughts and wonders about the vastness of the universe and the intricacies of Einstein's theory of relativity. I want to invite you to take action, to be part of a community that values knowledge, curiosity, and the endless pursuit of understanding. If today's episode sparked your interest, ignited a conversation, or simply offered you a moment of intellectual escape, I encourage you to support the English Plus podcast. By following us and sharing our content with your family and friends, you help us grow and reach more curious minds like yours. Your engagement is what keeps this podcast alive and thriving. But don't stop there. Take your support a step further by becoming a patron on Patreon. This isn't just about supporting the podcast, it's an opportunity for you to unlock a world of premium content. As a patron, you gain access to exclusive episodes, deep dives into fascinating topics, and a chance to be part of a community that's as passionate about learning as you are. Your support, whether it's through following, sharing, or becoming a patron, means the world to us. It enables us to continue creating content that enlightens, entertains, and educates. So take that step, join our journey of exploration and discovery, and become an integral part of the English Plus podcast community. Thank you for tuning in to today's episode. Your presence and engagement are what makes this journey so rewarding. Until next time, keep exploring, keep questioning, and keep sharing the wonder of learning with those around you. This is Danny signing off from the English Plus podcast. Stay curious, and I'll see you in the next episode.